Hi, everybody. Welcome to JuliaHub's webinar, Tools for Nonlinear Model Predictive Control. I'm Misha Saint-Amand. I'm the Director of Marketing for JuliaHub, and I'm joined today by our presenter, Dr. Ranjan Anantharaman. Ranjan holds a PhD in mathematics and computational science from MIT. At JuliaHub, he helps customers leverage modern computational methods through JuliaSim as a sales engineer. We're also joined today by Dr. Frederick Begge Carlson. He is the lead of the JuliaSim Control systems team at JuliaHub. He'll be in the background answering questions in the Q&A interface for you. So without any further ado, I'll pass things off to Ranjan to get things started.
Well, thanks, Misha, for the introduction. So hi, everybody. My name is Ranjan. I work as a sales engineer at JuliaHub. And today, I just want to go over JuliaSim. JuliaSim is JuliaHub's modeling and simulation product. And very specifically, I wanted to go through model-predictive control with JuliaSim. So in this webinar, I'm just going to cover these three main topics. The first being what really is JuliaSim and how exactly might an engineer or a modeling and simulation engineer leverage JuliaSim for their everyday work. And specifically, what is JuliaSim Control? So controls is a module within JuliaSim, and how exactly can you build controllers, optimize controllers, and synthesize controllers using JuliaSim. And once I get into that, I would like to then show you a little demo about how one might design a nonlinear model predictive controller that takes a model of a car and then performs lane changes autonomously. So the car would be listening to control inputs, which we would then tune using numerical methods, and it would learn how to follow a particular preordained reference trajectory. But it would do so autonomously without any external input. All right, but first, let's talk about JuliaSim and the specific tagline here: scientific machine learning for enterprise. So there's a bit to unpack here. So what exactly is scientific machine learning? So of course, there are lots of modeling and simulation tools that exist out there. But JuliaSim is the modeling and simulation tool that focuses on productizing for enterprise this idea called scientific machine learning. So scientific machine learning, sort of informally can be thought of as the interplay, the interplay between scientific computing and machine learning. So machine learning, of course, is sort of ballooned and grown incredibly over the last 10 to 15 years. But recently in the research world, there's been a sort of emphasis on what exactly does machine learning look like when applied to the physical sciences. So what exactly does quote unquote AI look like for the physical world, right? And scientific machine learning is a sort of answer to that. And of course, it is not the only answer to that, but this is a answer to that. So to give you a sort of more fine-grained look at what scientific machine learning is, think about the blocks of scientific computing first. So let's say you're trying to design a particular pipe in which a fluid flows. You would then construct a model of the pipe, the model of the fluid, and you would think about interactions between the pipe and the fluid, right? So there's an aspect there that involves building models, right? And of course these are derived from the physics and are set up in a programming language or an environment, right? And once you have this model built, you then think about discretizing and then solving this model. So in the fluid dynamics case, you would use some sort of finite volume or finite element type mesh type simulation to be able to simulate this, right? And now once you have that model and you then have parameters in the model, and you would like to analyze the model by looking at simulation data coming from the model at various instances of parameters, right? And once you have an idea of how this model behaves across its parameter regime, you might want to control it, right? So you might want to add a controller that either stabilizes this or makes makes the system reach a particular reference trajectory or a particular steady state. And so these are the sort of rough blocks of scientific computing and engineering in general, right? Now, machine learning, if you look at machine learning on the other hand, and those types of ideas, right? You would have a massive neural network that is massively over parameterized, and this neural network, through epochs and epochs of training, might learn a way of classifying cats from dogs, might learn a way of capturing time series, might learn a way of conducting reasoning, let's say via Bayesian analysis and Bayesian modeling. And of course, the foundation of most of machine learning is automatic differentiation, where you would take you would propagate the derivatives from a loss function, which is some sort of functional across all the parameters and the data that you're trying to learn from, and propagate those derivatives down to the individual parameters in your system. All right. So these two might sound like completely different verticals, but in the scientific machine learning domain, these are sort of combined in interesting ways in order to help engineers start designing the next generation of models. So what do I mean by that? Differentiable simulators, right? So can you design a physical system with parameters and easily be able to get the derivatives of some functional that's coming from the system with respect to its individual parameters, right? Can you sort of extend the idea of reverse automatic differentiation from machine learning to physical simulators, right? That's a sort of philosophical push. Now, with scientific machine learning, one might argue, well, you already know there are some classical techniques that already do some of this stuff, right? So if you think of the adjoint method, it's an adjoint method is a way of getting the derivatives of some of model outputs with respect to parameters, and that scales to thousands or millions of parameters, and it's a beautifully scalable method, right? This not only incorporates or not only considers classical techniques like those, but it sort of blends it with new techniques. So, for example, in scientific machine learning, you would use automatic differentiation or a program synthesized version of a derivative of your simulator, right? Which is a far newer technique than the old adjoint method. And so what this does is it not only it complements these old techniques with new techniques from program synthesis and compiler analysis to be able to provide differentiable simulators. So as you build a model, the compiler internally knows how to synthesize a program which is the derivative of this particular physical simulation, right? So the next sort of thing one might think about is reduced order modeling, right? So there are all sorts of classical techniques, projection-based model or reduction techniques, like proper orthogonal decomposition. And now what scientific machine learning does is tries to combine those with data-driven methods, such as, in this case, surrogate modeling. And of course, there are many kinds of surrogate modeling methods that are old and have been used for decades. But what scientific machine learning does is tries to bring in new techniques like echo state networks and and in particular continuous analogs of echo state networks, which are completely new to the reduced order modeling conversation. And of course, now that you have differentiable simulators, then inverse problems can then be done at the program level, as opposed to you the engineer having to automatically write down the inverse problem for any particular problem, or write down the inverse operator and then work on generating derivatives for calibration, right? So scientific machine learning tries to sort of combine both of these two worlds. The last sort of thing I'd mention before I quickly move on is automatic equation discovery. So if you have a model that you've designed, but it doesn't quite fit real world data that you're collecting from the factory or the clinic and stuff like that, you might be missing some physics. Can you use the state of the art system identification and machine learning techniques to be able to discover new physics? and to augment those physics with your model. And so, of course, so scientific machine learning tries to really think about how exactly you might take advances from computer science and machine learning and add them to scientific computing. So why am I telling you about scientific machine learning? JuliaSim is scientific machine learning for enterprise. So if you're ever thinking about, well, I like these machine learning tools, but I wanna be able to use them. JuliaSim is the right sort of suite of tools for you, right? If you want, what we try to do is be able to support all the classic modeling and simulation tasks. So for example, you want to build a model from scratch, you can then rely on JuliaSim's pre-made model libraries where you can drag and drop. You can, of course, then of course you can simulate these with the state-of-the-art solvers, some of which are proprietary to JuliaSim. And of course, we have a very rich suite of open source solvers that come from the Julia language as well, which we support. If you want to build models from scratch from data, then we have a suite of system identification techniques and digital twins, which you can then build a model to be able to use in downstream analysis. If you have models, but you then want to build cheaper versions of these models, we have reduced order modeling techniques and surrogate modeling techniques that you might want to take a look at. Of course, you need to think about where you might want to apply these reduced order modeling techniques in order to use them well, right? And if you have models and you have data coming from the factory, as I just mentioned before, you can use our proprietary model optimizer and model calibration techniques, which can then augment. You have a data-driven or a parameter-fitted model version of your model, a tuned version of your model, which you can then deploy as a sort of a digital twin as well. So we have a number of different techniques, some of which are classical and some which are modern, for all kinds of workflows that you might have. And that's basically what JuliaSim is about, to be able to bring these state-of-the-art techniques to the enterprise. All right. Now, what JuliaSim is sort of built upon is a modeling suite called Modeling Toolkit, which is how we sort of import. When I was talking about importing pre-made models and then sort of tying them together and simulating them, that's all done in this framework called Modeling Toolkit. Modeling Toolkit has a standard library which has inputs, mechanical components, electrical components, and a bunch of other things which you can import from. You don't need to build, of course, these models from scratch, and you can run them with our sort of proprietary state-of-the-art solver. And of course, I told you about model optimizer as well, where you can take models and calibrate them to data that are coming from the factory in the lab, create online digital twins, data augmented digital twins. This module, for example, specializes in large nonlinear problems, which are of course the hardest class of problems you might want to calibrate models to, right? Today's webinar is about controls. So can you take a model that you've designed and you want to do you want to either drive this model into a particular steady state, or you want to cause this model to reject disturbances, right? So can you design a controller which can do either of those two things, right? And very specifically, I want to talk about the system here on the right, which is a model predictive controller. Now, to give you a sort of very quick overview of what I mean by a model predictive controller, this has two components, right? So you have the original system here. So in some sense, I would call this a dynamical system or a plant model, or those are the words I would use to describe this, right? This system takes some inputs, has some system response, and these system response are what you see, which are what you can measure from the system. So these are measurements that you can acquire from the system. Of course, these measurements are literally have something to do with the system, but may not be the states. They are some sort of preordained outputs from the system. Using these outputs, you then have a state estimation algorithm, which then estimates the state of the system, right? So a Kalman filter or a particle filter or something like that. And this state estimation and measurements go back into the controller. And now this controller has a model of the system, It has, it has an online sort of digital twin of this system. And this model is used for prediction. So given a measurement and given a state, what is the next likely state of the system given a control action, right? So so if you have a space of control actions, what is the best control action to choose such that some objective is satisfied, right? And you do this in a stage process. So you start at t = 0, you have a prediction from the model, but this prediction is not so great given your objective. Therefore, you optimize and find a better prediction, and then you send that to the system, right? And you do this in increments increments of 0.1 seconds, 1 second, or microseconds, depending on the frequency that you design, right? Right. So that's what we're going to talk about today. So before I get into it again, so I should mention that JuliaSim is built on top of an enterprise computing platform called JuliaHub, which is a cloud platform, right? You sort of write code on the cloud platform. You spawn off jobs. You spawn off jobs that require a specific amount of compute, and this is a platform that is tuned towards bursts of computation. You've designed a beautiful new model and you wanted to simulate, but you don't want to stop doing what you're doing. You spawn off a job using JuliaHub and it simulates for you. So there's an aspect of the cloud that's sort of built into workflows here. And this is where I'm going to sort of demo, and I'll tease at all the various aspects where you can leverage the cloud while I'm showing you the demo, especially in case of simulation oriented tasks, and especially in this case model predictive control type tasks, right? Type analysis. So so like the sort of workflow we try to enable is to be able to start with a model, import it from any sort of environment that you might want to, design a controller on top of it, and of course, if you don't want to design a controller, you can do either build a surrogate or you can calibrate this model, right? But let's start talking about controls now. So I showed you the slide a little bit earlier, and in particular, I focused on the model predictive control side. But I also want to mention that you can do all the standard linear control analysis, right? And much of that is in the open source, right? So you can look at controlsystems.jl. You can look at this open source organization called Julia Control, which my colleague Frederick is actually maintains both our JuliaSim Control as well as the open source packages. But this is a fantastic suite of tools that lets you do all the standard linear controls analysis, linear model order reduction, and things like that. H-infinity design, all the things you might expect from to do linear control and robust control are all there, all there for you to actually go and try out right now. The model predictive control is specific to JuliaSim. And that's the part that I'm going to get into and show how to use today. But I do want to tell you that this stuff exists in the open source as well. So why would you want to design a model predictive controller using JuliaSim, right? So the nice thing about model predictive control is that you could use a linear or a nonlinear plant model, and at which with linear or nonlinear dynamics, right? So you have two options. You've built this beautiful model using modeling toolkit, which is our modeling and simulation base, right? You can then take this model and then either linearize it about some sort of operating point, right? In which case you'll get a linear model, or you could just use the nonlinear model directly in your model predictive controller, right? And of course that whether you choose a linear model or nonlinear model sort of affects the performance of the controller, and we'll get into that as well. But what you can, at every stage of this model predictive controller, right? So if you're running this model controller, if you're running a control action every 0.1 seconds, each control action is determined by an optimization problem. So the speed of that optimization problem is contingent or hinges upon the fact, as to whether you use a linear or a non-linear model, predictive model within your model predictive controller. So which is why you would sort of see that we say that you can solve linear model predictive controller problems at over 4,000 hertz, non-linear model predictive controller at a slight bump below at about 1000 hertz, because you need to solve these optimization problems in line in real time, right? And the one other thing you can do, again, that's very, very specific to JuliaSim, is build a surrogate of the controller. So as I mentioned, model predictive controller involves solving an optimization problem at each stage. And if you're sort of doing that, you can use data that you've gained from this optimization process, and then instead build a surrogate of this optimization loop, right? So if you build a surrogate, which is a direct mapping from parameters or control inputs to some output, then you get orders of magnitude speed, right? And we have examples to sort of show this. In fact, we have a whole new webinar which I will plug a little bit later, on where you can learn about how you can build surrogates of model predictive controllers, which my dear colleague Frederick has given, I think, about a month or two ago. I'll point you guys towards that. All right. Of course, we provide a bunch of robustness techniques as well. You can model uncertainties. You can obtain guaranteed constraint satisfaction. You can analyze performance using our tool sets. You can use these sort of binary or integer variables in your model predictive controls analysis. There are a lot of tools and techniques that you can use, which I will point you to. It's all there in the documentation. And part of what I will do is I will go through the documentation and show you where to find everything. Yes. So all of these tools that I've told you so far are things that you as a user gets on our platform and starts building, right? You either write code or use some of our other interfaces. But one thing we have for very common tasks are these apps. And this particular app is a PID auto tuning app. In addition to PID auto tuning, we also have a model auto reduction app as well, which lets you do balanced truncation. Do I have a slide on that? I don't think I have a slide on it, but that app does exist in addition to this. But what you can do is you can use this interface over here. So choose a desired frequency, choose certain parameters of the controller, and then you can start tuning this PID controller and sort of interactively in this GUI, and then look at whether you're able to satisfy your requirements, which is quite nice. So for some very common workflows, we have these apps set up, but for somewhat less common workflows or more custom workflows, we have a robust set of tools that you can build on top of. In addition to PID tuning PID controllers, you can perform tuning of other types of controllers, sort of arbitrary in structure with different requirements. You can model, again, parametric uncertainty and be robust to parametric uncertainty. And then again, there are a whole bunch of techniques in our documentation, which I will point you to on how all of this is possible. And if you have, by the way, if you have questions and stuff, please put them in the chat. And if there's anything I need to address, my colleague Frederick will answer a few of them. If there's anything I need to address on it, I will also do that. As I said earlier, we also have a model reduction app as well. So you're able to see. So for example, if you look at this particular app, we're doing balanced truncation, and we're choosing the order, right? We're sort of computing the singular values, and we're trying to then look at how do we choose the cutoff point for the order of the controller, right? And that's something that you can do interactively via this app. So if you have a large modeling toolkit model which you've built up, you've performed a linearization, but again the plant model is still too expensive to simulate, you can use a sort of automated model or reduction technique, which you can then design using this app and then deploy so as to be able to sort of expedited to use for sort of expedited control design, right? Of course, there are there are other things you can other things you can do for expedited control design as well. But we'll get into them a little later. All right. Again, as I said, there are a bunch of techniques for robust control also. So robust control. Also, I'm so I can get into the example. I am going to skip over this a little bit, but and I will just point you to documentation and examples on that do all these things. Pole placement methods. Again, as I mentioned earlier, H infinity methods, LQG methods. All of these things are possible within our suite of tools. I will point you to them. We also support a bunch of system identification techniques, trimming techniques to help you decide these operating points that you might want to linearize around, extremum seeking controls, self-optimizing controls, again, virtual sensors, so just a bag full of features that you might want to use for your analysis and design. Okay, so at this point, before I go on to the demo, I just want to check if there are any questions. Let me see if I can. So Frederick or Misha, if there are any questions that I might need to sort of address on air, just let me know. I can get to them.
Sure, Ranjan. No questions so far. Thank you.
Okay, sounds good. So maybe I'll just get into it. All right, cool. So what we're going to do today is look at nonlinear model predictive control. So you have a nonlinear plant model which we're not going to linearize, right? We are not going to perform any sort of linearization of this model, but we're just going to use this model directly as the predictive model and then design a controller. And let me show you exactly what that means. But before I go to code, I first want to sort of plug. I just want to plug our prior webinar, which does, our prior webinar, which talks about trimming, linearization, and model predictive control using a linear model, right? Which my colleague Frederick and my colleague Avinash gave a couple of months ago. You should be able to find this on our website. But I guess the first question perhaps I should address is, why would you want to use a nonlinear model, or why do you want to use nonlinear model predictive control as opposed to linear model predictive control? You don't need to perform linearization. You can just use nonlinear dynamics, which is nice. So you're not constrained to a particular kind of behavior about an operating point. So that's one, right? The second thing is you can use a cost function that is more interpretable, like something that actually has to do with actual cost of the system, right? Like running cost or or dollar cost in some sense. So something far more interpretable, right? So whereas in the linear MPC case, you're sort of using quadratic cost, which you may or may not want to use. So nonlinear MPC gives you more flexibility that way. You can also use nonlinear constraints. So you can whoops, sorry, I don't know why this text doesn't look right, but you can also use sort of nonlinear constraints for your optimization problem, and we will look at all these, and we will look at the specification through our API. Much of this has also been covered in the MPC tutorial. So if you're looking at all of these techniques, which might be part of your standard workflow, I would refer you to that particular webinar. The other thing that webinar covers, which is fantastic, is being able to generate a surrogate of the MPC controller, which is also something that's really cool, and you all should check out if you get a chance. Right. Now let's go on to this particular example that we're going to discuss today. Right? So what we're going to do is we're going to take a simplistic model of a car. So this model is called the kinematic bicycle model. It has 4 states. So this is just a 2D model first, right? So there's only X and Y, and it's moving from left to right. Right? This car is moving from left to right with a particular velocity and steering angle, which controls the X and the Y. Now, what this car, how we're going to control this car is via changing its acceleration and its these things look exactly the same. Sorry, but this is the steering angle. This is the orientation, actually, the first one. So apologies for that error there. So let me just change that right now. Oops. call that orientation. That's important. Can't have a state and you can't have the state and the controls be the same. That's weird. Anyway, so you have the acceleration and the steering angle, and you have one parameter here, which is the sort of the distance between the front and the back wheel. And you see it's a simple sort of four-dimensional dynamical system, which is given by these equations. Okay, so one of the steps, one of the first steps actually is to define this dynamical system, which is why I sort of led with that. But now that you have the dynamical system and you want to control it, what are the various steps to design a controller? Right? So first, you need to decide what is the reference path that you wanted to follow. So can I then say, okay, I wanted to change from lane 3 to lane 1 and then go back to lane 2. So can I design a particular trajectory that this car is supposed to follow? Right? That's the first thing. The second thing is the rest of these steps are everything to do with setting up an optimization problem, right? And you can already see where I'm going with this, right? So you have an optimization problem where the loss is the difference between some sort of difference, right? Some sort of distance between the reference trajectory and the true trajectory of the car, right? And of course, this is a constrained optimization problem. So let's define a few constraints. What are the typical kinds of constraints we might define? Bounds constraints. So what are the minimum and maximum values of the states? So I don't want the car to go. I don't want the car to leave the road, for example, right? And that's a consideration here. And what are the maximum and minimal values of the control inputs? So I don't want to increase. I don't want to increase the acceleration very quickly, or I don't want to increase the velocity very quickly because that results in jerky behavior. Of course, nobody wants a jerky car, so to speak. And can I then add some sort of terminal constraint? So I know where and how this car starts out, but where and how does this car end? What is the final position of the car? And that is something you can add as a terminal constraint. So you can see we do have a primitive for this, the terminal constraint primitive, and you can see that while designing other types of controllers where you want a system to be constrained to a particular type of steady state, you might see how this type of constraint is useful for that. That's its own, that's a independent line of thought. We can talk about that separately. Okay, so once you define the constraint, very quickly, let's define the cost function. So now that you have a reference trajectory, the cost function is obvious. You need to sort of penalize the deviation from the reference. And one other thing we do for stability of the the controller and the car is to penalize large control signals. So to again avoid jerk. So you want to penalize the value of acceleration and penalize the value of the steering angle. Right? You don't want it to you don't want sudden increases of in velocity and steering angle. Next, now that we have these things, we then set up this optimization problem and throw all our costs and constraints and dynamics into this MPC problem, and then you solve the problem. Right? And so now that I've sort of described the various steps to design the controller, let's perhaps look at some code. Okay, and before I go to code, I also wanted to just quickly show you this URL, juliahub.com/resources/webinars, where you can find all of our webinars. So if you're thinking about Frederick's webinar from a while ago, here it is, trimming, linearization, and MPC. If you click on this, you should then you should be able to get this webinar for free. Right? That's where you get that information. Okay. So having shown you that, let's go to JuliaSim. Actually, this is this is your the home for JuliaSim. So you see you have JuliaHub, where you can start off a set of jobs. You can choose a bunch of applications. So you scroll through, we have a lot of different kinds of applications here, and then you can launch a particular cloud job. I'm currently on our internal thing, and you see we have a bunch of different applications, some of which might be relevant and not. But again, you can launch a cloud instance with a precompiled version of Julia and all the libraries, so that you can then start playing with it. But once you launch a job from over there, you are then taken to this type of interface, which is an IDE firstly. So an IDE where you sort of write code. Now, so one question we've gotten, in prior webinars is, hey, do we have a graphical user interface to be able to specify these models and design these controllers? We don't have one right now, but we are going to have one by the summer. So please stay tuned for that. You should be able to see some sort of graphical user interface to be able to design all these things, by the summer. And of course, it'll have all the components and all the models. And so that's the first thing. The second thing is, can you try these? Can you try this example out right now? Yes, you can. We have a free version of our offerings that's going out with a limited amount of compute. You can go to JuliaHub and try to sign up right now and see if you're able to get the free version. If not, you should be able to get it in a month or so. That is where you can try these things out for free, and see how, and for example, you can try out this example. Okay, so let's go back to designing a nonlinear MPC. So what's the first step? So the first step is to load a bunch of packages. So the ones that we're loading are JuliaSim Control, specifically the MPC module from there. And then we are loading a few others, and I'll show you how these others are referenced. Plotting makes sense. We also make use of this other package called static arrays, which are which are sort of faster implementations of regular arrays, which come in handy in some situations. Well, we can talk about that if you have a question about what static arrays are separately. Right? So again, what's the first thing we want to do is to design a reference trajectory. Okay, so in this particular case, we're using this package called trajectory limiters. It's an open source package, which my colleague Frederick has written, where you take a nonlinear, you sort of take a predefined reference trajectory and then use a filter to be able to then generate an actual reference trajectory. So what do I mean by that? Right? What I mean by that is, let's say you have maximum values of acceleration and velocity and a particular sample time, because of course these things are discrete. Let's then define a reference trajectory that is just a simple function of time. But if you notice that this function in time has a sine function, so this is a sine function has a discontinuity at the point where it changes sign, right? So in order to smooth out these discontinuities, that's what trajectory limiters does. So you have maximum values of, again, as I said, maximum values of acceleration and velocity, a particular sample frequency, which of course we're going to use for the MPC and everything. In this case, it's 0.1. So you take this particular trajectory, we have a 30-second time window, and we then use this particular limiter, this trajectory limiter technique, to be able to find a smooth version of this trajectory. So let me sort of plot it out and show you what that means. So you should be able to see this plot now. You see here that the original trajectory that we gave trajectory limiters.jl is this dashed line over here. So you see that this is basically a square signal, but we don't want a car to follow a square signal. So we smooth out these discontinuities nicely. We sort of smooth these transitions out so that the lane changes can be quite smooth. So that's what I mean. So the trajectory limiters takes this dashed line as input and gives you this solid line as output. All right. So now that we've defined the trajectory, our next step is to define the dynamics. So the dynamics, as I said, are is just an implementation of the 4 ODEs I showed you earlier, right? So this is a simple kinematic bicycle model of the car, excuse me, and this is a simple straight line definition of those dynamics. Okay. Now Our next step is to define the number of states and number of inputs and number of outputs. So in this case, our states are our outputs. So that's why you see 3 and 3 here. Then which is x, y, and this phi here. Then you see, then what are our control inputs, right? What are the dimensions of control inputs? And that's 2. So so the next sort of big assumption that we're making, just again for the simplicity of this example, is the measurement function. Now here we are assuming that we can measure the states directly. Usually we cannot, but in this particular situation we assume that we can just directly measure the states. Okay, so let me just run through some of this code. Some of this code is mostly bookkeeping, as the number of states and stuff like that. So we're providing little labels for what our states and what our states are. And then we're defining something called a function system. Now, a function system has 2 things. It has the dynamics as its first argument, and some measurement that is coming from the dynamics as a second argument. Okay, so if you've used differential equations.jl, you might be working, or modeling toolkit, you might be working with an ODE system, which is just the dynamical system. But in the controls case, this function system is an idea or a concept that goes above that, right? Which is dynamics in addition to some form of measurement. Okay. Now, MPC is a sort of discrete method. So one thing we need to do is, once we have a continuous dynamical system, we need to perform some sort of discretization. And in this case, we're using the Rangakoda 4 discretization to be able to discretize it at a frequency of 0.1. And really what we're designing a controller to do is to be able to figure out via an optimization process, what are the control signals that need to be fed into the system every 0.1 seconds, right? So that's the regime we're operating in, right? Now, next set of bookkeeping is to design the initial condition of the system and the initial condition of the reference trajectory. So again, this is just some bookkeeping that we've done. The next step is to design constraints. So as I said earlier, we have 2 types of constraints here: bounds constraints, which are to do with the maximum and minimum value of the state, and the terminal constraint as to where we want the system to finish at, right? So if you look at look at this, you'll see that we have limits for the we have lower limits and upper limits for our state itself. And this, of course, this is taking into account things like don't go off the road. And the next thing we have are these control limits. What are the maximum and minimum values of the control space I want to search? You could sort of think of it in conjunction with whenever you're performing some sort of global optimization method, you're usually thinking about upper and lower bounds. You're sort of searching for globally optimum parameters within some region, some sort of Cartesian region, which are defined by upper and lower bounds of the parameters. So you can sort of you can think of these UMIN and UMAX as some sort of analog to that, because this is a region in which you want to find your optimal control inputs. Okay. So so I'm also adding some scaling constants so that this optimization problem is a bit smoother. I just want to glance over that for a second. These things are usually the unnamed heroes in having these methods converge quickly, but I'll skip over them for now. So once you have those bounds constraints, right, you put them in an object called the bounds constraint object. And so you see here, you can see in my terminal down here that I've just initialized these with xmin, xmax, umin, umax. Okay. Now, once I've specified my constraints, the next thing I need to do is to specify specify my loss function. Of course, I'm running an optimization loop. I need to specify some cost function. So what is this cost? So the first thing you might notice is there's something called stage cost. So one nice thing you see about our IDE is that as soon as you sort of pass the cursor over a particular object, you can get its documentation, right? So in model predictive control, we're finding optimal inputs at every at a sort of receding, let's say at a fixed frequency, so to speak, right? So the optimization tries to find optimal control inputs at a particular fixed frequency. Now, this stage cost is a way of expressing that. So what do I mean? Here, in this stage cost, we are at every stage of the system. We're calling this a running cost object, but this represents that at every stage of the MPC problem, we are then computing some sort of distance between the original system and the reference trajectory, right? So or the simulation and the reference trajectory. So we're penalizing it with this distance. So interestingly enough, this particular cost is actually quadratic. Actually, the rest of this cost is quadratic in this particular case. But you see that here we're penalizing this, and we're and with the other states we're penalizing it to different extents, and we're also penalizing large control signals, right? So we don't want these control signals to be overtly large, and we don't want the problems to bleed out like that. Okay. The next thing we're going to do is we're trying to penalize the differences in control action. So what we don't want is at one particular stage, we have a particular value of a control signal. And the next stage, we have a much substantially different value of a control signal. So this code, adds a difference cost. So it computes the difference between the current current control action and the control action from the previous time period, and penalizes large differences there. So we'd like these changes in control actions to be as smooth as possible. And that's what these two lines of code do, and they penalize this. So you see that we have two kinds of running costs. So two kinds of cost functions. So the first is the stage cost, and the second action is the difference cost. And now that we have these two costs, we can initialize an object called objective, which incorporates both of these costs, which I've done here. Now, the last constraint is a terminal constraint. The terminal constraint is a way of saying what I want the simulation or what I want the model to end at, right? If you can look at this over here, if you look at the reference over here, you see that the final position at the end of the simulation is in this position y equals 1.5, right? And we're sort of trying to have a constraint. We're trying to penalize or rather encapsulate a constraint where our car ends at the correct terminal condition. So that's what this terminal constraint is called. So basically, you see, we've set up the objective function, and now we're adding constraints. And that's really what's going on. It's sort of this elaborate way of setting up an optimization problem. All right. Now, once we do that, we should initialize this optimization problem. And so the way we do that is to say it should take the way we do that is through this object called objective input, which is again just a way of initializing the optimization problem. So what do we do here? We have a 30-second time window. We've split this 30-second time window up into intervals of 0.1 second each. And so we're and we're grouping some of these time windows up, right? So so you see that we have n is equal to 30. So we're taking these 300 mini windows and grouping them up into a total, so 10 windows each. So that it's 30 windows of 10 mini windows each, right? And the reason we're doing that is because we're trying to optimize across each of these 30 windows. So the way that works is you have this X over here, which is just an initial condition. You have U over here, which is the initial condition for the initial condition for the controls. And what we're then doing is then we're rolling out these dynamics such that if you give these initial conditions, what exactly will the X's and U's look like, right? And we're sort of capturing this all in this objective input function. So once you capture it, once you've set up or initialize this optimization problem, right? And of course, you can initialize it in any which way. This is the specific way we've chosen to initialize it. The last and final stage before you set it up is to define an observer. So remember how I told you once you have a control action that goes into the system, you need to have an observer that collects some output from the system and then gives it back to the predictive model. If you recall my diagram, and this observer, the observer that we're using in this particular example is an idealized observer. So it's an observer that, as you can see in the screen here, directly gets the states from the system. So it's able to, so this is basically an idealized oracle, right? So usually you won't be able to get the true state of the system. But just again, to illustrate this example, we use this thing called a state feedback controller, which is an idealized version, which is able to get the exact state of the system. Okay. So once you do that, you then set up the discretization. You set up you set up the solver again with a number of different tolerances. Excuse me. Of different tolerances, and of course you can. It's fairly obvious what each of these arguments are doing. But once you've set up all these various solver parameters, in this case we're using IP-awk, you can then throw that into a large problem, a generic model predictive control problem. So this is of course a subtype of this is a subtype of other types of model predictive control. But here this generic model predictive controller problem is to be able to take a model predictive control problem without any sort of specializations in it, right? So this is the catch-all general version. So here's where this is the type of interface you use to specify a nonlinear MPC problem. So you see all the various, like we've defined about 20 things, right? But all of those 20 things are all going into this problem here. This discretization, the time set discretization, the parameters, the scaling factors, how one might generate Jacobians, all your constraints and objectives and observers, all of them are encapsulated in this problem. And now once you finally put everything into a problem, you get a nice little, some nice logs here actually, once that's done, which you can see, which describes the MPC problem with the right solver and the observer. But once you've set up the problem, you can then finally hit solve. But before I hit solve, I want to set up a little animation here, and I do this via a callback function. And this callback function just plots the frame of the trajectory, plots the trajectory as it is being optimized for, right? So let me just show you the animation instead of describing it. So this is going to take a second, and while this is taking a second, I'll take another sip of water. So you can see that this dashed line over here is the prediction, but this dotted line over here is the reference. So you see that this is very sort of neatly following the reference insofar as it can. Okay, so that's how we know that this is doing exactly what we want it to do. Of course, we can analyze So again, instead of looking at this, you can sort of analyze this in a more conventional sense and look at the plotted, outputs. Just look at the plotted outputs directly. You can also, you can plot it against the reference that it's supposed to follow. It's doing it quite well. And of course, you can plot all the control inputs, the optimal control inputs that are happening at every stage as well. So, so again, you can analyze this quite nicely. And to sort of round this off, I wanted to show you one final animation of the car actually moving and changing lanes, which is quite nice. Yeah, it's taking a second, but you can see here that our car here is sort of autonomously changing lanes quite nicely, which is nice to see. Our car's doing a nice little job. All right, so at this stage, I should pause again and ask for questions. I think my colleague Frederick's doing a great job of answering these questions as they come in the chat, because I'm not able to see them. So actually, we're sort of hitting the hour mark. So what I'm going to do is quickly round this off and then conclude with questions. The final sort of takeaway message I wanted to give you is here. I just gave you a sense of what it takes to use our control suite, which is quite nice. But of course, JuliaSim has many more modules. So in addition to controls, which in itself is like a really rich set of tools, we have so many other tools that we can sort of work with you and provide for you to be able to use in your analysis. So you want to generate surrogates, you want to calibrate your models, you want to use our proprietary solvers, you want to build models, or you want to use one of our apps. JuliaSim is sort of has something for you. But I thought I am at the hour mark though, so with that, perhaps I shall conclude and see if there are any questions.
Thank you, Ranjan, for the very nice presentation. We have had a few questions along the webinar, but they have been answered. So okay. I would like to encourage anyone who has any remaining questions to please type them in the Q&A box and we'll answer them live.
Yes. So now I'm going to open up the Q&A box so that I can take a look. Okay, so I see one question. How does machine learning come into the simulator? So maybe let me just answer that live. So there are a few ways where so in the specific example that I showed you right now, there is no machine learning. It's just how would you build a control system given a model, right? Which is a more classical thing. But machine learning, the way you would use machine learning in perhaps many contexts, and let me answer in the context of JuliaSim, is you can then once you have the simulator, you can then generate data and then come up with a reduced order model, right? And that's what the surrogatizer does. So that's one aspect of machine learning. The other aspect of machine learning is, let's say I've now designed, in this example itself, right? I've designed this MPC controller, but this MPC controller is running too slowly. What I can then do is, instead of running the optimization problem every time, I can then learn a surrogate that sort of removes the need for running that optimization problem, right? So it's a direct map to optimal control functions. So given from measurements and from inputs that goes into the predictive model, what are the what are the optimal control functions, and you can of course learn some of these things in theory online as well. So that's the other way you could incorporate machine learning. And of course there are other ways. If you had a model but it didn't, like of course we had this car bicycle model, but of course it's not a real car. We can get road measurement data and then discover quote unquote unknown physics, right, to be able to do it in some sense. And those types of system identification techniques these days tend to be very machine learning based. So that's a third way machine learning could be incorporated into this analysis. So there are plenty of ways, and yeah, it really depends on what you want to do. Okay, so I'm sure. Okay, so the next question I see is, so should we design and incorporate machine learning modules by ourselves? So yeah, so I see, yeah, so let's again just to repeat the question: should we design and incorporate machine learning models by ourselves? So the answer is yes and no, right? So the no part of the answer is we have okay, I'll let Frederick chime in there as well, but the no part of the answer is we have automated sort of interfaces to do all this design for you, right? That's part of why we're offering this. We are putting a bunch of things. Sorry, we're giving you a bunch of high-level interfaces in order to train these machine learning models, and so you don't have to do most of the work. But the parts that you need to think about are how you might use the machine learning models. And of course, we have plenty of documentation, plenty of ways to help a designer decide what they might want to use these models for. But that's a question that is on the modeling side and not necessarily on the tool side. What the tool does is makes it easy for you. But why you might want to use it and what you use it for are things that you must, like, you as a modeler should probably convince yourself of. But of course, we sort of help assist with that. So if there's a particular idea you have in the context of if you're wondering, oh, can I apply these latest machine learning techniques to this problem of mine? Feel free to either look at our documentation to see our prospective workflows, or to get in touch with us, and we will help you design a very specific solution for you. Okay. Next.
I'm just going to jump in here. I know we have a couple more questions coming in. We should probably wrap it after these two.
Okay. Sounds good. Thanks, Misha. So can system identification techniques work in offline mode? So I see Frederick is typing an answer to that. So I'm going to let him do that while I answer the next one. Is there a functionality of nonlinear system identification prior to wrapping an MPC around it? Of course, we don't have a model for a certain only input-output data. Yes, there is. Thank you, Hamza. Sorry, I probably should not read out the name of the person who asked me, but thank you for answering this question. The answer is yes. So what you can do is, once you have a model, you can then use our model discovery workflows and pipeline to be able to then add physics and extra terms to your model, right? So that's the system identification step. So once you run it through model discovery, you can then get a new model, which is a combination of these data-driven terms in the model. And now that you have this these sort of data augmented model, you could then wrap a controller around it into MPC and all of that. So yes, you absolutely can do that. That is definitely possible. I think that's.
Well, I thank everybody for submitting the questions, and for Ranjan for presenting, and Frederick for answering questions. We very much appreciate you being here. There are plenty of more resources on controls, both webinars on our website, as well as some great YouTube content that Frederick has created. And we look forward to, hopefully you'll come and visit and learn a little bit more and get some more information. We also have another upcoming controls webinar coming next month, and I'll be sharing that in the follow-up email that will include the recording of this webinar. So thank you all for joining us. Thank you to our presenters, and we look forward to seeing you at another JuliaHub event soon.
Thank you. And if you guys want documentation, it's on help.juliahub.com. It's all open, so you all can check it out. There's a lot of good information there.
Along with the recording, I'll make sure I put that in, as well as a few other links we discussed. Thanks, everybody.